Hello and welcome to the second in the series of the 2020 EREFCOM webinars. Firstly, I would like to acknowledge my co-authors of this paper and the numerous colleagues who contributed to its preparation. The information in this webinar was first presented at the 2016 AFPM annual meeting and at subsequent meetings and conferences with other sponsors. This is really a story of how one refiner worked with their catalyst supplier to devise and implement a program to measure, to monitor, and to mitigate the effects of iron in the FCC. We'll start with looking at some background information on the effects of iron poisoning on FCC catalyst, as well as unit operation and yields. We'll also cover specific events that were the origin of this paper. And finally, we'll discuss a variety of methods to manage iron in the FCC unit. Iron poisoning of FCC catalyst is not a new phenomenon and was first recognized by refiners as far back as the 1990s. Historically, FCC feeds have been low in iron. The growth of domestic crude, specifically tight oils, has resulted in novel challenges. Iron is reactive with other FCC contaminants, forming a barrier layer on the Ecat, thereby preventing hydrocarbon reactants and products from diffusing through the catalyst to and from the cracking sites. This leads to reduced conversion, increased yields of low-value products. The barrier layer presents as nodule morphology. Furthermore, the iron complex nodules on the surface of the catalyst can disrupt catalyst fluidization through a decrease in circulating catalyst bulk density, reducing the head pressure required for adequate catalyst circulation, and in turn, further reducing conversion. Nodules can be observed and analyzed through SEM analysis. The nodules reduce the amount of catalyst that can pack into a given space, creating a reduction in the ABD. We should note that iron is present in the FCC catalyst as an element in the clay used in the manufacturing process. Hence, the iron content of the fresh catalyst is dependent on the clay source and the clay content of the catalyst, and this will vary among suppliers as well as catalyst types. It's important to look at the incremental rather than the total iron on catalyst, since the iron from clay does not affect catalytic performance. If the iron level of the fresh catalyst is known, incremental iron can be monitored. Since iron poisoning mostly affects the surface of the catalyst, as seen in the cross-sectional mapping figure at the bottom of the slide, surface area and pore volume may not necessarily change. Previous studies have shown that finely dispersed iron particles can be organic or colloidal. Inorganic particles that will deposit onto the surface of the catalyst. Tramp iron from sources such as rusting refinery equipment will not affect catalyst quality. Deposited iron combines with silica, with calcium, sodium, and other contaminants to form low melting temperature phases. These create nodules that occlude the catalyst surface, limiting diffusion of hydrocarbons through the catalyst particle. Iron may also cause dehydrogenation reactions. However, it's estimated to have 10 times less effect than contaminant nickel. Since PES FCCs had high levels of nickel, so up to 5,000 ppm, the dehydrogenation reactions separately attributed to iron were not apparent. As we'll see in the next slide, the refiner did face high levels of calcium during these iron events. Calcium also deposits on the catalyst surface and can contribute to blocking the pores. This leads to decreased conversion and increased bottoms yields. As Ecats had very high levels of calcium, as seen in the 2013 GRACE database for North American FCC Unit Ecat analysis. High levels of calcium may reduce the iron tolerance of the catalyst. Therefore, the PES catalysts were potentially susceptible to poisoning of iron from much lower levels. Other factors that can affect iron tolerance are catalyst type and riser residence time. A unit with a shorter residence time is more susceptible to iron poisoning, since the oil may not be able to travel into the catalyst particle and fully crack with the diffusion limits the contaminant iron pose. While iron can be present in many crudes, it can be found to be especially common in tight oil-derived feeds. PES protocol had been set up to sample all incoming crudes, and in the limited time that PES had been testing crude sources, it became apparent that iron could be variable within a specific crude. Large iron spikes can have significant consequences. Let's take a moment and talk about the two FCC units that PES operated at the Philadelphia refinery. The 868 unit, shown on the left, was a KBR orthoflow design. and operated with full CO combustion in the regenerator with a moderate level of resid in the Ecat Fe. The normal fresh feed weight was approximately 50 mbpd. The unit designated as 1232, shown at the right, was a Kellogg Model 3 side-by-side design operating within partial CO combustion, processing high levels of resid from a 2-refinery complex with a large catalyst inventory. This unit was charging as much as 100 mbpd of fresh feed. The first event occurred in March 2013 at the Point Breeze FCC, Unit 868, which experienced severe fluidization problems. The 868 unit is a full-burn unit with the disengager located above the regenerator. In this design, the catalyst traveled from the disengager stripper down a large internal catalyst standpipe to a plug valve before entering the regenerator. The fluidization disruption in March 2013 manifested itself in the form of an increase in disengager stripper level. The operations team were able to temporarily resolve the issue by reducing riser temperature and unit charge rate to slow down the catalyst circulation. PES experienced an ion spike in the 868 unit, which is the moderate resid cracker. The impact is evident in the catalyst samples collected during that time, both from the FCC circulating inventory as well as from the ESP fines downstream of the regenerator. The Ecat had turned brown. This is versus a normal expected gray color. And this provided visual confirmation of high levels of iron. The fines collected from the ESP also turned a brownish hue during this time frame. Analysis of the circulating inventory showed an Ecat ion concentration increase of 0.27 weight% within a month and 0.14% within a week. And the source of ion was traced back to the crude. SEM scans confirmed the expected abnormal morphology that is detrimental to catalyst circulation. The apparent bulk density, or ABD, of the catalyst decreased by more than 0.05 during this time frame and dropped off significantly at levels over 0.65 weight% total ion on the catalyst. Minor fluidization issues persisted until the catalyst addition rates were increased to flush out the contaminant metals and restore fluidization properties. For years, Ecat ion did not fluctuate much, and it wasn't consequential. However, a second event occurred in June 2014, this time at the 1232 resid cracker, resulting in increased slurry yields, lower than expected resid processing, and catalyst circulation limits. During the increase in ion on the catalyst circulation rates were seen in the form of low slide valve differential pressures. The 1232 unit had a large slanted regenerator catalyst standpipe with 10 aeration nozzles. The aeration nozzles were adjusted several times in an attempt to improve circulation, however only with minor benefits. Due to the higher than modeled slurry yields, as seen in the bottom right-hand plot, a root cause failure analysis was launched. This comprehensive review included checking for feed and slurry leaks, feed atomization, catalyst circulation problems, feed quality, fractionator tower performance, fresh catalyst quality, purchased Ecat quality, as well as the catalyst loader reliability. Adding to the complexity of the high ion and reduced resid processing was a catalyst change just prior to the event. As the ion increased on the catalyst, Grace used SEM analysis to monitor the health of the catalyst. SEM pictures suggested that Grace's Midas Gold FCC catalyst had superior resistance to ion complex nodule formation than did the base catalyst, as the morphology is improved despite the same or even higher levels of iron or calcium. Grace also utilized an analytical technique called the effective diffusivity test, which tracked well with the changes in Ecat ion concentration and unit performance. Please note that diffusivity measurement is a troubleshooting tool. This is not a fresh catalyst property. Catalyst diffusivity becomes an important factor when there are changes occurring. It's a leading indicator that bad things are going to happen because the quality of the catalyst inside the unit has become compromised. In this case, PES was forced to reduce resid. The lower right-hand plot shows the impact of residue processing. Roughly 10 mbpd of resid was cut out during the processing limits and was restored when ion levels dropped. Now let's move on to discuss all of the methods used to overcome the effects of ion poisoning. These methods were a combination of preventative, routine monitoring, and actions to help lessen the detrimental effects. The testing feed stream in crude oil provided valuable information to help drive adjustments such as catalyst addition rate. ASTM's D5708 utilizes inductively coupled plasma, or ICP, to measure the metal content in the oil. There are two methods of sample preparation. Method A dissolves the sample in an organic solvent, while method B uses an acid to digest the sample. The acid digestion method, method B, will measure the total metal content, whereas the solvent digestion method A will detect metals present in the insoluble particles. The total amount of iron showed roughly 30% higher in the acid digestion method. However, it varied over the course of the samples. Use of this method helped close catalyst balances and help drive resolution steps. Reducing iron to the FCC by all means possible can prove to be a very cost-effective step. Managing corrosion in the refinery is not only a good safety practice, and it can also limit the iron to the FCC. Desalting alone can help remove some iron, however, desalting will not remove organic iron. Desalt or acidification has also been documented to enhance oil-to-water separation, leading to lower salt, sediment, and water in the desalted crude, as well as with the removal of some metal contaminants in the crude. Those contaminants tend to end up in the heavier cuts and fed to the FCC. This was especially true with the PES case, who charged resid to both FCC units. The use of wetting agents can help drop out solids, including colloidal particles of iron and calcium from the crude oil. Removing calcium from the FCC feedstock as well as sodium can reduce the degree of iron poisoning, since these metals combine to limit diffusion. Desalt or acidification has shown great success at removing calcium from crude oil. As shown in the figure at the top, it has also shown modest levels of iron removal. Shale oils tend to have solids that contain high amounts of calcium and iron. Therefore, it's desirable to knock these solids out if possible prior to the FCC unit. Solid wetting agents or removal agents can help drop solids, including colloidal particles of iron and calcium, into the water phase, helping to remove these particles. The additive can also improve desalter operation by reducing solids and emulsion buildup inside the desalter, leading to improved salter residence time. Now we'll look at the monitoring and evaluation of the Ecat and unit performance, along with some important selection criteria for the catalyst that was used at the PES 1232 Cat unit. Prior to adding Midas Gold catalyst to the 1232 unit, we set up a collaborative program with the refiner to monitor various performance aspects. Both routine and non-standard analytical techniques, for example, the SEM analysis that we showed earlier, were deployed. For several aspects of catalyst and unit performance, some of which are listed here, we established a response and action matrix to prepare for any changes in unit operation that may require a catalyst adjustment. One example is shown here for the plans to place to monitor various aspects relating to fluidization in the 1232 unit. As was observed on the 868 unit, the apparent bulk density fell with increasing levels of contaminant iron at the 1232 unit. The new catalyst was able to maintain a higher ABD at equivalent iron on the Ecat. This was particularly helpful from a fluidization standpoint. One important example of non-routine catalyst testing was the measure of catalyst diffusivity. The GRACE effective diffusivity test proved to be more an accurate reflection of the actual changes to both catalyst and yield, most importantly during the iron excursions of 2014. The results obtained within this test were consistent and a reliable indicator of the effects of iron, particularly when the threshold level was reached. One solution to manage iron levels on the Ecat, of course, is with increased catalyst addition rate. Higher rates will also purge other contaminants. However, using purchased Ecat to supplement fresh catalyst may be a more economical solution for large inventory resid processing units. When adding high levels of both fresh and purchased Ecat, a loader capable of adding multiple components provides the most flexibility to properly balance those addition rates. Any purchased Ecat should be complementary to desired unit yields. Most refiners have relatively simple criteria for selecting purchased Ecats. Here we're showing the quality of the bulk Ecat in green with the purchased Ecat in blue. We can also see the activity of the 1232 unit purchased Ecat regularly matches that of the bulk Ecat. But early on, the zeolite to matrix surface area was not appropriate for the target yields. PES changed their purchased Ecat catalyst selection to more closely match the bulk Ecat ZSA to MSA ratio in order to optimize bottoms cracking in the resid operation. In the same way, the zeolite unit cell size was brought in line to reflect the desired hydrogen transfer characteristics. An iron on purchased Ecat was reduced in line with minimizing the overall iron on the Ecat in the inventory. Selection of a cracking catalyst with proper underlying fundamentals is a key for both bottoms cracking and iron resistance. Compared to the base catalyst, Midas catalysts, as shown here, are richer in mesopores that serve to optimize hydrocarbon diffusion by more than a factor of 2. And at the same time, Midas catalysts minimize smaller micropores, which are diffusion hindered. Cracking that occurs in those small micropores increases gas and catalytic coke due to diffusion limitations. The Midas Gold catalyst used at 1232 unit helped to improve catalyst stability in the face of various contaminants and improve fluidization, as measured by the ratio of minimum bubbling and minimum fluidization velocity, even at higher levels of iron on the Ecat. As catalyst suppliers, we must always maintain a focus on the F in FCC. Improving the fluidization characteristics of the catalyst was especially important in this older unit design with long sloping standpipes. By managing iron in the unit inventory, profitability can be maintained while processing opportunity crudes. Analytically, we drew from a wide repertoire of test methods to successfully monitor the performance in the 1232 unit. Selection of a catalyst with optimized porosity helped to mitigate problems with iron. And if you do use purchased Ecat catalyst to supplement fresh additions, the selectivity of that material should complement overall unit activity. Thank you very much for your time.